how can we determine the length of a curve? Now, we are going to assume that the curve has a path, but in order for us to actually define the length of a curve, we need to make some assumptions about the path that we're using. We're going to define something called a smooth path. And if we have a curve that has a vector function r that takes it from some interval on the real line to r3, we are going to say that r is smoothly parametrized if the following are true. If r prime of t is continuous for all t in that interval a to b, and if r prime of t is never 0 for all t in that interval a to b. Now, you might say, why do we need to care about this? I'll try to illustrate this to you. So if I give you a path that has t squared I plus t cubed j, and this is a path that takes us from r into r2. Now note that x is equal to t squared, which is the same as saying t cubed to the power of 2/3. X is y to the 2/3. So the kind of curve that we get here has something that looks like this. If you were to pick values of t, as t increases, that means y increases as well. So there is a direction to this parametrization. If I wanted to find r prime of t, I have 2ti plus 3t squared j. Now, r equals 0 when t is at the origin. That's one possible answer. The derivative equals 0 when t is equal to 0 as well. Now, what's happening here? The derivative represents the tangent to the curve at a given point. The tangent has no direction when I'm at this location. If I were to talk about the secant lines on this side, if I were to take secant slopes over on this side, here the tangent vector is pointing outward, but here the tangent vector is pointing this way. So what happens is that there's a sudden change in the tangent direction when this r prime is equal to 0. And that's why we don't want to have that possible. In our definition of a smooth path, we are eliminating this possibility. So a curve with a smooth path is called a smooth curve. In order to be called a smooth curve, not all of the paths need to be smooth. You just have to have one smooth path. Now, an additional constraint that we're going to put in is that distinct points from the open interval a to b will map to distinct points in R3, except possibly when t is equal to a or t is equal to b. We will traverse our curve only once. So if you're talking about a smooth curve, we're talking about things with nice, well-defined tangents. We do not have cusps. Those correspond to spots where the derivative vector is 0. Things with loop-de-loops are no good because there are two different times at which you can get to that point. And closed curves like this are okay because you could possibly repeat yourself at that endpoint only once. So with that in mind, we are going to talk about the length of a curve. We are going to assume we have a smooth path. R of t is equal to this f of t, g of t, h of t. To be smooth, that means each one of these functions here has a derivative, and the derivative is continuous. So if we wanted to talk about the length of a curve, we are going to subdivide this curve into straight line segments. This point corresponds to the initial time, whereas this point corresponds to the last time. We are going to take a series of points for our t value and work our way down. Ti is given by the recipe A plus I delta t. And what we're going to do is subdivide this curve into these time values and then connect them with straight lines. This will be segment 1, and segment 1 is going to have its own length, and segment 2 and segment 3. And then we'll say that the length is approximately the sum of all of these little individual segments. We're going to assume delta t is constant, and then we're going to shrink this delta t down to 0, and that's going to help us define the actual length of this curve. So we're going to zoom in on the curve, and we'll say this point right here corresponds to the position at time I minus 1, and this point right here corresponds to the position at time I. There's the straight line segment between them, and it has a length Li. So Li is the length of the displacement vector that connects those 2 points. So it's the length of r at ti subtract r at ti minus 1. Now, I could take this Li, multiply and divide everything by a delta t. R of ti minus r of ti minus 1 over delta t, and then multiplied with delta t. Now, in each one of these cases, this delta t is a positive number and it's a constant. According to properties of vector lengths, because this is a positive number, and now if I were to consider each of these, this is where the assumptions that I've made are going to come into play here. Because I have a smooth curve, this path has a continuous derivative. That means the derivative exists. That tells me that this function r is differentiable. If the function is differentiable, by properties of calculus, it also has to be continuous. And because it's continuous, the mean value theorem applies. Now remember, when you've got a vector function, it's made up of 3 scalar components. If the vector function is differentiable and has continuous derivatives, it means each component has a continuous derivative. That means each component is differentiable. That means each component is continuous, and that means the mean value theorem applies to each component of this vector function r. So according to that, I can rewrite this Li as r prime at some ti star times this delta t. And so the total length is then approximately the sum, I equals 1 to n, of all of these individual lengths, which is essentially the sum, I equals 1 to n, of this r prime at ti star, length of that vector times delta t. As this delta t goes to 0, this is essentially just a Riemann sum. By the fundamental theorem of calculus, turns into a definite integral. And so we will define the length of a curve to be the limit as delta t goes to 0 of the sum I equals 1 to n, the derivative of the length, delta t, we know turns into an integral. And it's going to be an integral of r prime of t length dt. This is our definition for how to calculate the length of a particular curve. This is essentially like speed and essentially like time. The length or the distance is kind of like speed times time. It's relatively straightforward to apply it to a variety of paths for different curves. Now, here is a path that's been given to us. We don't know what the curve is. In order for us to use the arc length formula, we've got to make sure we have a smooth path. Well, in this particular case, we get a 12i, we're going to get a 12t in the j, and we'll get a 6t in the k. Each one of these components is continuous on the interval 0 to 1. Oh, I apologize. This is a 1/2. And that means then that r prime is continuous on this 0 to 1. That's the first condition of being a smooth path. R prime of t will never be 0, because if you look at the x component, this is a constant, and it's never equal to 0. It's impossible for r prime vector to equal the 0 vector. So this corresponds to a smooth path for this curve. Now remember, I don't know what the curve is. It's not really important here. The length of this curve is going to be an integral from 0 to 1. Now, I've already computed the r prime vector. It's going to be the square root of 12 squared plus 12 to the 1/2 squared plus 6t squared dt. So this is going to give me an integral 0 to 1 square root of 144 plus 144t plus 36t squared. Now, it turns out that integrals for arc length are notoriously difficult to evaluate directly because of the presence of the square root. In this particular case, there's a common factor of 36 that I can pull out from the root. This will give me a 4 plus a 4t plus a t squared dt. This will end up giving me a square root 36. The quantity inside the bracket is t plus 2 all squared. This ends up giving me absolute value of 6, absolute value of t plus 2. This is positive on the interval 0 to 1. So this integral is simply 6 into t plus 2 dt. So at the end of the day, this is going to give you a 6 times a t squared over 2 plus a 2t evaluated from 0 to 1. So that's 6 into a half plus 2. So you're going to get 6 into 5 over 2, which is going to be 15. So if I have a circle of radius r, I would love to figure out the distance around the circle. So here we're going to take a path, one that goes 0 to 2 pi into r2, and this path will be given by r cosine of t, r sine of t. This was discussed in the previous video. The derivative of this path is going to be negative r sine t, r cos t, and you can see for yourself that each component of the derivative exists. Each component is continuous, and note r1 prime will never equal the 0 vector because the spots where sine is equal to 0 are not the same as the spots where cosine is equal to 0. So it's impossible for you to get both of them equal to 0 together. The length of this curve will be from 0 to 2 pi. I will take the length of this r1 derivative and integrate it. Now, in this particular case, I'll go from 0 to 2 pi, and I'll have the square root of negative r sine t squared, r cos t squared dt. This is going to give me an r squared into sine squared of t plus cos squared of t. And I know that this quantity is equal to 1. This is going to give me a 0 to 2 pi square root of r squared dt. This is going to be an integral 0 to 2 pi r, because that quantity is positive, dt. So as expected, this gives me the circumference of a circle. The length around the edge of a circle is 2 pi r. Now note, if I were to use this other path, r2 is the cosine of 2t, sine of 2t, I have to be a little bit careful. If I use this time interval 0 to 2 pi, that means I'm going to go around the circle twice. That would violate one of those additional conditions where we said we only want to traverse the curve once. So that means we need an interval from 0 to pi, because this would ensure that we go around the circle once. And if I were to do that, I would take the derivative r2 prime of t. I would get negative 2r sine of 2t, and I would get 2r cos of 2t. If I were to take the length of this quantity, 4r squared sine squared 2t plus cos squared 2t, which is going to end up giving me a 2r, because this quantity is equal to 1. So this would be an integral from 0 to pi of 2r dt, which as expected gives me the same result. Now this is a good example of the next important point. The length of the curve should not depend on the path. That's our intuition. It doesn't matter which mathematical description we use. The length is somehow intrinsic to the curve.